So, good morning, students. The next topic that we would like to discuss is the calculation of certain thermodynamic parameter that we can calculate easily with the help of, we can say, partition functions. So, first one is the internal energy. The internal energy U of a system of molecules is given by the equation U equal to summation EI into Ni, and is equal to putting the value of Ni from the previous Boltzmann equations, EI into N by F e to the minus EI by KT. And you know N and F are the constant quantity, N is the total number of the particles and F is the partition function, so they will comes out from the summation sign. So the U equal to N by F summation EI e to the minus EI by KT. But we know F, that is partition function, equal to summation e to the power minus ei by kt. So if I differentiate this equation with respect to t, this becomes df by dt equal to 1 upon kt square summation ei e to the power minus ei by kt. This is the simply e to the power minus mx type formula. So using this formula you will get this thing. So summation ei e to the power minus ei by kt equal to kt square df by dt. Okay, now substituting the internal energy value U equal to N by F summation EI into e to the power minus EI by K. So U equal to N by F summation EI e to the power minus EI by KT equal to putting the value of summation EI e to the power minus EI by KT equal to KT square by KT square into df by dt. That means N KT square by F df by dt, or you can say N KT square df by F means d of ln F, so N KT square d ln F by dt. And for 1 gram mole, if I multiply this quantity by the Avogadro's number N0, we'll get the internal energy for 1 mole of the gas molecule. So U equal to N naught KT square d ln F by dt, where N is the Avogadro's number. And the average energy of each molecule E average equal to KT square d ln F by dt. Next quantity is the entropy, and we know that S equal to that equation is also coming from the Boltzmann equation. So S equal to N K ln F plus K beta into U, and we know that also beta equal to 1 upon KT. So we have S equal to N K ln F plus U, and putting the value of beta KT, so U by T. Okay, so substituting the value of U from the previous equation, we get S equal to N K ln F plus N K T d ln F by dt. Next function is the work function, and we know that a equal to u minus ts. Here I have to mention a is also known as Helmholtz function or work function. So a equal to u minus ts. Using u and s in terms of the partition function as expressed above, we can write a equal to u minus t, and putting the value of s from this equation nk ln f plus u by t. So a equal to u minus t into nk ln f, and then t cancel out, minus u and u cancel, so remaining terms is minus nkt ln f. And we know that a equal to u minus ts, so dA equal to du minus tds minus s dt. So if I little bit arrange these things, du minus tds equal to minus pdv from the first law and say combine second law equation minus sdt. So if I differentiate this equation dA by dV at constant temperature, then this term will 0 and it gives the minus of P. So P equal to minus of dA by dV at constant temperature. And we know that A is not a direct function of V, so we can bypass this equation by taking dA by dF into dF by dt at constant temperature. So A becomes minus nkt ln F, that is dA by dF at since we know A equal to minus nkt ln F, so dA by dF at constant temperature equal to minus nkt ln F. Okay, so putting this value, we get P equal to initially it was minus dA by dF, so its value is minus nkt by F, minus nkt by F, and the previous sign of minus and this minus cancel out into dF by dV at constant temperature. And we can little bit manipulate this thing because dF by F means d of ln F, so nkt d of ln F by dV at constant temperature. And the third one is the Gibbs potential, and we know that G equal to H minus Ts, this is the Gibbs function. I expand the equation of H as U plus PV minus Ts, and you know that if I arrange U minus Ts plus PV in this form, then this quantity becomes A, because A equal to U minus Ts. So A plus PV, so G equal to A plus PV, and we can write G equal to A, the value of A is coming from this equation minus nkt ln F plus nkt, putting d ln F by dV, because the value of PV So putting the value of A and PV from the previous equation, G equal to minus NKT ln A plus NKT, this is the value of P multiplied. If I multiplied this equation by V, this terms becomes NKT d ln A by dV multiplied by V. So now taking the common as minus NKT, so this term becomes only ln F minus d ln F by d ln V, so taking the common of minus nkt, this term becomes n f only minus d ln f, that is initially here, and if I arrange this thing by dv by v, then it becomes d of ln v at constant temperature. So this is the final form of the Gibbs potential. And the fourth one is the heat content, or H, or sometimes it is known as enthalpy. The heat content H equal to U plus PV. By definition we know that, and H equal to, putting the value of U from the previous equation, equal to nkt square into d ln f by dt, and the value of PV is nkt d ln f by dv multiplied by V. So taking common nkt, this term becomes d ln f by dt upon t. So this is totally becomes d ln t plus d ln f by d ln v, because this is also I just explained in the previous video, dv by v equal to d of ln v. So this is the final form of the heat content or enthalpy. And the heat capacity, by definition we know that Cv equal to du by dt at constant V, because when a gas molecule undergoes heat change at constant volume condition, that amount is called Cv. So Cv equal to nk. If I differentiate this equation of U, that is we have performed in the previous. So putting the value of U in this equation ddt of U, we will get the value of Cv, and we know that from the previous translation equation, that means from here I can say where it goes, U equal to nkt square d ln f by dt. This is the value of U. So putting this value we will get here Cv equal to nk, it is the constant term comes out, ddt of t square d ln f, here f is the f translation, okay, so f translation by dt, and the value of f translation is coming from this equation directly. So ln f translation equal to this constant quantity plus ln 3 by ln t 3 by 2. So if I differentiate this f translation, ln f translation, it gives me 3 by 2 into 1 upon t. So putting this value directly here, I can get nk becomes r, so r ddt of t square, and the value of ddt of ln f equal to 3 by 2 into 1 upon t. So this t gives me only t, so 3 by 2 is a constant term, so it will comes out from this differentiation. So 3 by 2 r ddt of t, and we know that ddt of t is 1, so 3 by 2 into r. So this is the value of the heat capacity at constant